Let's consider y equals the square root of x. Now, we're going to take the derivative, y prime, it's x to the 1/2, so you get 1 over 2 root x. Okay, so when we're looking at the critical points of this function, we'd set it equal to 0, and there's no number where it's equal to 0. But look at the denominator. The derivative cannot have a denominator of 0. Now you can in the original function, x can be 0. So what actually happens here when the denominator is 0? Okay, as you get smaller and smaller values of x, the derivative becomes larger and larger and larger. So what you end up with is a vertical slope. Now the square root of x looks like this, and you're going to have technically a vertical slope right there at 0, 0. So do note critically that 0 is defined in the domain, but it is not with the derivative. So when you're finding your critical point, you do need to set the denominator equal to 0 and look at it. We'll look at an example where you have a vertical asymptote instead. The difference is that in the vertical asymptote, it's not going to be defined in the original function. So what we're actually going to do is we're going to put everything together, domains, limits, derivatives, second derivatives, to graph an additional function. So let's consider the example f of x equals 3x squared over x squared minus 1. Now the first thing that you should consider when graphing a function, what's in the domain? Okay, and the default should be that the domain is all real numbers. So what you really want to look at is what's excluded from the domain. Like in this example, negative numbers would be excluded. So calculus, the first study, this class, introductory calculus, is the calculus of real numbers. The calculus of complex numbers is actually a separate branch, which is typically studied by math majors in college. So for the domain for this one, we're taking everything except, also we can't have a denominator equal to 0, so x is everything except plus or minus 1. Okay, so that's the domain. Other standard things that you look for, like what are the intercepts? For instance, what's f of 0? Okay, f of 0, just plug in and you get 0. So when you plug in x equals 0, okay, which is what we did, right? X is 0. That's right in the middle, and the idea is it gives you the y-intercept, okay? So that's the y-intercept. Now for the x-intercept, you would set the whole thing equal to 0, okay? So for the x-intercept, you would basically set, the whole function, 3x squared, sorry about that, 3x squared over x squared minus 1 equals 0. And what do we get? You get the same thing. Because this function equals 0 when x equals 0. Okay, so these are two different things. You could have plugged in 0. If we put a plus 1 there, then you would get 1 for the y-intercept. And so this equals 0 when x equals 0. Okay, so the y-intercept and the x-intercept are in fact the same in this case. We've got the y-intercept, the x-intercept, and the domain, okay? That's 3 critical parts of the function. Now what about the asymptotes? How do we actually get the asymptotes of a function? So we talked a little bit about this before. If you remember, we have the limit as x approaches infinity. That's going to give us an asymptote. It's of this function. So it's of what you're trying to graph, 3x squared over x squared minus 1. And if you remember, you divide everything by x squared, you take the largest power, you just get 3 over 1. And so this is in fact 3. Okay, if this is not familiar, There's a previous video about this. You also want to check it at negative infinity, and so you're going to do the limit as x approaches negative infinity. And in this particular case, it's going to be the same thing. Why is it the same thing? It's because it's just x squared. And if it's just x squared, then positive or negative infinity is not going to matter. And it is going to also be 3. Okay, so we're getting the same asymptote in both directions. So these are sort of the standard non-calculus things that you do. Now, something else that you need to do, so basically these are the horizontal asymptotes, okay, horizontal, we'll just say here somewhere. Horizontal asymptotes. Now what about the vertical asymptotes, right? The vertical asymptotes are when x approaches a certain number and then you get infinity, right? So in effect, the limit as x approaches what of 3x squared over x squared minus 1 will give us infinity. Okay, right? So how do we figure this out? In effect, you're looking at the denominator, okay? You're basically solving the denominator to be equal to 0. It's these points, the plus or minus 1. Now note the difference. In this particular case, 0 is defined in the domain. This one it's not, okay? So we want to look at what happens as x approaches 1. Now what's interesting about these is you've got to consider it from the right and the left, okay? Because coming out one from one direction and one from the other direction can give you a different infinity. Okay, so let's consider positive 1 from the right. Okay, well what happens? This is putting in values that are larger than 1. Okay, we're just going to make our denominator positive, so it is positive infinity. Okay, that checks out. Now, what if we do it the other way? What if we do the limit as x approaches 1 from the left? Okay, well let's check it out. Function up here. I mean, simply put, when you're going from the left, if you look at the denominator is going to be a value that's slightly less than 1. It's going to be negative. The numerator is just going to be positive. It's always going to be positive. X squared is always positive, but when it's less than 1, you get a negative denominator. So this is negative infinity. Now, let's check it carefully for negative 1, which is also not defined here, meaning the domain gives you 0. So let's check x approaches negative 1 and start from the right of our function. Now, if you're coming at it from the right, okay, you got to think about what's the number that you're putting in. It's like a number like negative 0.999, right? You square it, you get the same thing, but that denominator is going to be negative because when you square it's going to be less than 1. So this one's actually negative infinity, and you can basically predict what x equals negative 1 from the left should be, and that is going to be, let's just check it. So if you're plugging in negative 1 from the left, it's like negative 1.1, say, and you're getting values that are larger in the denominator, making the denominator positive, which makes this a positive infinity. Okay, hopefully that negative is clear up there. Make it a little clearer. Negative infinity. Okay, this is great. So we got a lot of info. All that's really left now is to do the derivatives. And let's see what we get when we take the derivatives and set it equal to 0, because we need to find the critical points. Okay, so f prime of x equals what? Well, we got to use the quotient rule here, it looks like. So let's just go ahead and do it. Derivative of the numerator is 6x times the denominator, x squared minus 1, minus the derivative of the denominator, that's 2x, times the numerator, that's 3x squared, all over the denominator squared. Now we set that equal to 0, and what do we get? It's kind of interesting. So if you look at this, the numerator in effect is what we're looking at, because denominator doesn't count, cross multiply, it's gone. And all the terms have an x with it. You know what I mean? You could multiply it out. You know, should we multiply it out to be on the safe side? Let's just maybe to be on the safe side. What do we get if we multiply it out? We get 6x cubed minus 6x minus 6x cubed, right? And if you set that equal to 0, you're gonna have like 2 of the 6x cubes. Wait, no, they cancel out. That's cool. They cancel out, and you just get negative 6x equals 0. And that clearly equals 0. That implies x is 0. So we have a critical point at x equals 0. Now, you can consider like the 1 and negative 1 also. It can be worth looking at. So if we make our line here and then we put in for, really 0 is the only one that we really need to consider, but we'll go ahead and put in the denominator. Okay, so we have this 1 and negative 1. And what we're doing now is we're looking at, for the derivative, okay, we're going to plug in the values and see if it's increasing or decreasing, right? If the derivative is positive, it's going up. If the derivative is negative, it's going down. So we're just looking at the derivative here, okay? So if we take, let's take a value greater than 1, okay? We're going up here, like 2. Okay, well, what happens? What do we get? The way that numerator is written, it's not, I think what we want to look at, okay, it canceled out to basically negative 6x, right? And when we get the negative 6x, it should be over x squared minus 1 over 2. So let me just write that up here, because it simplifies, it's going to make this easier. So we end up with a negative 6x over this x squared minus 1. And so we lost the x squared minus 1 because we're solving for 0. But when we want to see what happens, we need to take that into account. Okay, so put in a number like 2. Okay, positive denominator, negative numerator. So this is negative. Now, what happens if we put in a number like 1/2? If we put in a number like 1/2, did I do this right? Let me check. So if we put in a number like 2, positive, negative, we put in a number like 1/2, we're going to get a negative. Oh, see, the denominator is always positive. That's what it is. So it's also negative. And then anytime we put in negatives, okay, it's going to be positive. Okay, so that tells us where the function is increasing and decreasing. Okay? Now, all that's left are the points of concavity. Then we're going to put all of this together to do one big graph. Okay, so we're going to try it, and we're right here, f double prime of x. Okay? Okay, and let me just be clear that this is f prime of x. Okay, so now what's f double prime of x? It's obviously easier to take this derivative than that big thing. Okay, derivative of the numerator is negative 6, right? Derivative of the times the denominator, that's the x squared minus 1 squared, minus the derivative of the denominator. We're going to use the chain rule, so we've got 2x squared minus 1 times 2x, all times the numerator, which is negative 6x. That's all over the denominator squared. Okay, so for the denominator squared, we get x squared minus 1 all squared, but it's squared, so that's to the 4th. Okay, so this is a little bit messy, so let's try to simplify the numerator and see what we get. Now, I'm going to try something here. So you see how we've got an x squared minus 1? We've got 2 of them here and 1 of them here. It's almost like if you had y squared and y, you could factor out the y. So I'm going to go ahead and factor out an x squared minus 1. And what are we left with? We're left with negative 6 times another x squared minus 1. And then here we've just got the x squared minus 1 is factored out. The two negatives make a positive. We got a positive 4 times 6 is 24. And then we've got 2x is x squared. So just the numerator here. Okay, you should write the denominator, but sometimes I do this. We're going to simplify the numerator a little bit more, because when we factored this out, it's all factored. And we end up with x squared minus 1. And then we're going to have a negative 6x squared plus 24x squared. That's 18x squared. And then we're going to get a plus 6. Okay. And that's all over x squared minus 1 to the 4th. And we've got to still set this equal to 0, right? Because we're finding where it's concave up and concave down. Okay? So this is equal to 0 when either one of these numerators are in fact equal to, either one of these products in the numerator are equal to 0. Now, this first one, if you look at it, when will 18x squared plus 6 be equal to 0? Never. Why never? Well, you could try to solve it and you'll get something like 18x squared equals negative 6, x squared equals negative 1/3. No, you can't do that. This is always greater than 0. So it's only this term, x squared minus 1, and once again, we get the plus or minus 1, right? Because we solved this for 0, we've already done that, that's plus or minus 1. So those end up being our critical points here, the negative 1 and 1. And this is simply to get the concavity. Where is it concave up and concave down? Okay, so if we look here, this is always positive, this is always positive. If you get a number greater than 1, yeah, this is positive. 0, this is negative. Remember, those two are always positive. And finally, the negative 2 is going to match the other side positive, so you get basically concave up, concave down, and concave up. Now, that's a lot of information, okay? What we still need to do, there's not really room up here, but we'll make some, is to actually graph it, okay? So we're actually going to graph this. I'm going to clear out this upper corner, and now we have everything that we need. Okay, so let's give it a look. All right. Okay, so here's our x and our y. Now, we have asymptotes here, right? So the vertical and horizontal asymptotes are negative plus or minus 1. Okay, so let's make that. So we got a plus 1 here, minus 1. Okay, so that's 1 and negative 1. Okay, what else do we have? We have our intercept 0, 0, so this is actually a point. And we also have our horizontal asymptotes, which is basically y equals 3, it's horizontal. So if that's 1, 3 might be somewhere up here. Okay, now, how do we figure the rest of this? Okay, so we got, I guess if we didn't write it down, but this, when the derivative goes from plus to minus, this is a max. So it's peaking right here, okay? That is a maximum point. So it's got to go down. And what we have is this whole interval from negative 1 to positive 1 is concave down, right? And we've got the asymptotes here, so we know it's going to go something like this, okay? Great, now what about these other sides to it? The other two we know are concave up, okay? Now, where exactly do we put these? Okay, we can look at our asymptotes. So if you're approaching 1 from the right, it goes to infinity, okay? And the horizontal asymptote goes to 3. So it's going to look like this. And similarly, if you look at the upper left, hopefully you can see it up here, it's going to go to, let's check it, if you come to -1 from the right, it goes to negative infinity, but if you come -1 to the left, it goes to positive infinity. And certainly as x goes to negative infinity, it goes to 3. So you end up with something like this. Okay, so you have nice symmetry on this. That is the complete graph. That is sort of a summary of like all the things that you can do to build and understand a graph from scratch using calculus.